mechanical loss is this one. Now, this one comes to the machine, right? This one is going to be equal to EA, IA. Actually, if you look at it, there are going to be core loss. You're going to have some losses, and hysteresis loss, eddy current loss, those kind of things inside the rotor. And now here, this is the electrical power coming to the machine. EA, IA. This is the electrical power coming to the machine. From this point, you're going to have an armature resistance loss. And you are going to have, if you have a garage sheet also, I can put it here. But you are going to have the garage also. And you are going to have the excitation loss. See, in this case, it is not separately excited to come from different sources. Everything is coming from here. Whatever is coming here is used here also. So it's going to be minus RF IF squared. And this is the P out. This is the VT IF. This is the output power. In case you want to calculate the efficiency, simply say A is equal to P out over P in. So you can say VTIL over, or you can say, other way you can say it is VTIL over VTIL. P loss. You can do it this way. So that's all the losses you have here. The P loss is equal to RAIA squared plus 2VBIA plus RF IF squared plus P core plus P rotation. You know this equation. This is the efficiency, the output power over the input power. So we're going to go through some examples now. Before we start, for all the cases, if the current is leaving the positive side of EA, means it's generator. If it's going this way, it's motor. Keep in mind, because we are going to start, in this example, I'm going to use this one. If the current is leaving the positive side of EA, is a generator. If it's entering to the positive side, is a motor. Now, it says we have a separately excited machine, so the excitation is separate excitation, and this machine is rotating at 3000 RPM. So it says the field current is constant. EA is 125 volt. RA is a 0.02 ohm. Now it said calculate, we're going to calculate IA PT, let's call it P terminal. We're going to see, I don't call it P out or P in because I don't know, it's a motor or generator. PT means, yeah, P terminal. We need to calculate the P terminal, but this is separately excited. PE and T. If VT is 128 volt, or if VT is 120 volt. We're going to calculate a very simple example, but a little bit practice the circuit of the slightly excited machine, how it does work. So we want to know first part A. Under these conditions, we want to calculate IA, PT, PE, and PE is here. Even they call this one PE. Yeah, let's call it. Yeah. We want to calculate this value parameters here. So can you tell me this is a motor or generator, part A? Because I need to draw the circuit and solve it, right? That's very simple, as simple as that. You know, just this is the circuit. I should solve it. You know, again, part A. I have excitation. Let's not do it this way. Let's just do it like this. UF IM RM. I'm not putting the direction of the current because that one is going to define it. This is a generator or motor. Now part A. Can you tell me, is it a motor or generator? Okay. This says motor. Why? Yeah. If you look at here, VT is how much? 128. This one is more than EA. How much is EA? It says here 125. So if you look at here, if this voltage is more than this, the current is going to go this way, right? So this one is going to be motor, right? So I'm going to put IA like this. For part A, IA is like that. So how much is the IA now? Very simple. IA is equal to VT minus EA over R, right? It doesn't say anything about the brush voltage, anything. I'm not putting any number over there. But if you had the brush voltages, for example, if it's 2 volts per brush, I'll put, for example, minus 2 VB, right? And it said each brush is 1 volt, so it said 2 volt here, I'll add that one. But in this case, it didn't tell us anything about the brush voltages, so I'll just put 0 here, okay? Now, just to calculate, it's going to be 128 minus 125 over how much was the RA? 0.12. So basically this one is going to be 150 amps. It says calculate the PT, P terminal. In this case, it's the input power. How much is the PT? VT, IA. Usually we call it IL, but you know in this machine, IL and IA they are the same, right? I input, you know. But I'm saying usually they use IA. So VT, IA, how much was it? 128 times 150. So this one is going to be, if this one is correct, it is 19.2 kilowatts. So, yes?
Sorry, I missed it. Can you tell me why ED was zero?
Because it didn't say anything. If it didn't give us any information about the brushes, you know, like if it doesn't mean you have to ignore it, just say ignore. Unless you tell us, for example, the drop voltage of the brushes is 1 volt, you know what I'm saying? So basically there's a 1 volt here, 1 volt here, you say, okay, I have a 2 volts, right? It's a 2 VB here, but it didn't say anything, just actually zero. Yeah, I'm saying the full complete equation is this. But because it didn't say anything, I ignored this part, just I put 0 for this. Now, if you look at it, how much is the PE, P electrical? You can say EA, IA, or you can say PT minus RA IA squared. Either way, right? You can say also the power is coming here minus the loss you have here is going to be here. So if you calculate this one, is going to be 18.70 5 kilowatt. The last thing is the developed torque. How much is the TE? Is the TE over omega, right? So how much is omega? It's in 3000 RPM. And you have to change it to the radian per second, right? So this one is going to be 8750 divided by to change the RPM to radian per second. First of all, you divide it first by 60 to have a what? RPS, right? RPS is the rotation per second. You know, first you should change the rotation per minute. RPM is the rotation per minute. You should change it to rotation per second, right? If it's for example 60 RPM, means every minute it rotates how many times? 60 times, right? So every second, how many times it rotates? 1, because every minute is 60 seconds, right? So first you calculate the RPS. You say, so RPM should be divided by, RPM divided by 60 is going to be RPS, right? Rotation per second. So every rotation for every rotation, how many radian it is? 2 pi. So times by 2 pi. RPS times 2 pi is a radian per second, right? Because I'm saying, just keep it in mind. 2 pi over 60 is the how to convert the RPM to the radian per second. So if you calculate this one, looks like it's going to end up 16 Newton meter. This one was a very simple example. Let's go to a little bit more on the shunt machine. Remember when we went over the shunt machine, I think it was Thursday, we said when we have a shunt machine, there is a one curve here, is the E versus IF, right? No load, right? And we have another one, which this one was E equal to what? RF IF, right? But this one was approximation because this basically is the VT equal to IF, right? Basically, we want to see the real equation. Was VT equal to this equation? Almost, because this is a no load. Keep in mind, it's a no load. This current is how much? Is 0, right? So basically, this current is not very big. So the drop here is not very big. We said almost. This one is equal to here. So keep this one in mind. We're going to go to the next example. It says a shunt machine has RF plus, I'll call it RF. The field excitation is RF is equal to, let me see what to calculate here. Yeah, RF, let's call it RF. Is equal to 20 ohm. RA is equal to 0.2 ohm, right? And this magnetization curve, the one I'm going to give you in the homework, is a table. Table basically we are giving you point by point. This one, this one, this one. We give you a few points like that. You have to go. Is a table. One axis is the EAF, one axis is IF. The one you are going to see in the book also. But here it is simplified for us. It says this machine has this no load characteristic is equal to 100 IF plus 1 if IF is less than 0.806 amp and is equal to 2IF plus AD if IF is more than, is more than 40. So this is a no load characteristic of this machine, and usually it should tell you what a speed it is, but here, I don't know what, but whatever speed it is. Usually this one is, it happened at a specific speed, right? Remember, we said this curve, if for example this is for 1000 RPM, if I reduce the speed of machine to, for example, I don't know, to 800 RPM, curve is going to be like this, right? Why? If you remember, we said E is equal to K flux omega, right? If you reduce the omega, see, let's say for IF, you can say KF IF omega. For example, for the same IF we had here, let's say, I don't know, this one was 1 amp, for example, right? If you are rotating machine at 1000 RPM, this much voltage will be generated, right? If I rotate the machine at a speed lower than that, the voltage will be less, right? Because you see, I'm saying keep the IF constant, KF is a constant. If you reduce the speed, the voltage is going to come down, right? So this curve they are given for a specific speed. But in this example, looks like we didn't need it, you know. Just as said, we have a shunt machine, it has a RF this much, RA this much. The no load curve is like this. Now let's see what is the rest. So, let me see what we have. It said calculate the terminal voltage of machine. What is the terminal voltage of machine at no load? At no load.
Yeah.
Hmm?
Yeah. What's the year?
How much is it? What number? You don't know. We have to calculate. Yeah, it's EA almost. Almost is EA. We are not calculating exactly how much is it, but how to calculate it. Let's see. So just I plot this one. See, this is my circuit, right? And how much is IL? How much is IL? 0, because it's a no load, right? How much is IA? I don't know. How much is EA? I don't know. How much is IF? We don't know. So we're going to find everything under the no load condition. It would be good practice to look at, hey, I said almost this one is equal to this one. Let's see how much error I have. There's some error here. Let's look at that one also in this example. So, how should I solve it? Any idea? Let me plot this one first. Let me plot this one first to look at it a little bit. So this is the IF and this is the EA, right? So let's say this is a 8.806. So if IF is less than this one, we are in this side, right? So if IF is 0, how much is this? EA is 1, right? Just put 0 IF here, EA is going to be 1. If you put IF, I don't know, 80.806, how much is EA? Times this one by 100 is going to be 80.6 plus 1 is going to be 81.6, right? So let's assume this one 81.6, right? This is the first part of the thing. Now, if IF is more than 806.806, it's going to be, we can find another point here. For example, if we put IF equals to 1, how much is this one? 882. So basically, 0.8. Almost very flat, you know, it's like 82, right? See here, when you change the IF, even if you make it 10, this one becomes 100, you know, is the saturated part. Now, tell me, you guys tell me what's the next equation? Right. What should I do next? Yeah. See, I have one equation here.